videos to walk through problem 1 of concrete form design 2. I choose walkthrough instead of go into detail with the lengthy videos, because this problem, the way what we solve, is similar to problem 3 in concrete form design 1 when we design for slab form design. So in this case, it's vertical form. So form AB in design for the 8-foot high concrete core to be placed at the rate of 4 feet per hour, internally vibrated and temperature 90 degrees. The concrete mixture will be used in type 1 cement without retarders and is estimated to weigh 150 pounds per cubic foot. Seating will be 4 by 8 feet sheet of 3-4 inch thick of glass 1 ply form with face grain perpendicular to stuck, and the finger is shown here, face grain perpendicular to stuck. Stuck and double wells will be 2 by 4 inch lumber. So stuck, as you can see, only one 2 by 4, and the wells is double of that, so 2 by 4 but 2 member of, so similar to the finger that we shown in this finger when you have stuck have double member in that problem. Snap tie are 3,000 pound capacity with 1.5 inch wide wedge bearing on the well, so 1.5, 1.5. So you have the wedge in there. Deflection must not exceed L over 360. Determine the stuck, well, and tie spacing. Use the pliform section properties and allowable stress from table 13.6 and lumber section property from table 13.3 in the book. And allowable stresses for the lumber being used for stuck and wells are as follows. So bending, shear, compression perpendicular to the face grain, support for 85, and the modulus of elasticity. So how can we do? First, similar to problem 3 in concrete form design 1, we need to determine the design load. But in that problem, the design load is vertical, so including the dead load and live load. That for the slab form we design, then the load have to be vertical. Now the vertical form, the load have to be the lateral, and that is the concrete pressure. So that is the difference in this case. So let's go to that one. So the first difference, design load in this is the concrete pressure, and with the rate of 4 feet per hour, then we can go to the exam reference, and for the walls in this case, the rate of vertical placement less than 7 feet per hour, and the height is less than 14 feet. Our problems, the height is 8 feet and the rate is 4, so it's exactly in that equation. So we can apply this equation here, and that go back to this problem. Bmax, and plug the number in, we get 550 pound per square foot. But it had to be in the range of minimum pressure, which is 600 CW, and CW in this case equal to 1, then 600 pound per square foot. What is CW? CC, we can go to the reference, and you can go back to the previous lesson, concrete form design 1, to go into detail to determine the CW and CC in problem 1 and problem 2 in that lessons. And then maximum pressure is 100% fluid WH, 150 times 8, 12,000. So our Pmax, if 550 is less than 600, so you will use 600 pound per square foot at a design load. Then the next step in the previous problem 3, we need to determine the deck design, which means select the joint spacing at the end, as you can see here. Now at analogies, the choice same as stuck, stringer, analogies to wells. short type. So with that, we go to the next step, select stuck spacing, and we consider the strip for the sitting is 1 foot, so it's 12 inches. So we can determine the uniform distributed load on the sitting, and that is 12 inches divided by 12 unit conversion to foot, 600 pound per square foot. So you have 600 pound per foot. And here we assume 3 or more spans, just like previous lessons, so that it can be a continuous support throughout for the sitting. And we can be able to use table 3.5 here with the bending, shear, and deflection, so that we can determine the spacings for the stud, and that we can have that here, bending. And yes, bending, go back to the reference for bending. This is a plywood, so we have to use 3 or more span and plywood, so we have to use this equation. Unlike in the previous problem, we use the first equation because the sitting in that case are the wood, not plywood, not engineer wood. So with that, we, instead of use the first equation on the last column, we use the third equation in the last column here, right? So because that plywood, then we can be able to find out the bending space for stud with regard to bending, and FBKS can be determined from table 13.6. What is table 13.6? That is the property for the plywood. So go to next table. That is section property of plywood, and you have that is KB, KS, and for face grain across the support of face grain parallel to support. So you can be able to determine that one. In this problem, they give us the face grain perpendicular to the stud, so you can get that one, face grain across the support. Okay, so that we can use KBS in this case with 3/4 plywood, class 1 plywood form. So you can be able to have FBKS 0.878 10 power 3 power inch per foot, so that we can plug in this equation, and here divide by W, 600 per pound foot we determine in the previous step, so that we can be able to determine 13.2 inch. So what is the face grain parallel or perpendicular to the support? I just show you the finger here so that you can be able to see the difference. So for the plywood or the wood, this is the face grain, and you can see typically in here, and the support is basically that is either stringer, joints, or stuck. Depends on what we are talking about, slab form or vertical form. In that, the first finger that you have, finger A here, that is the face grain perpendicular to the support. The support are the joints, so perpendicular to support, as you can see. And now if it parallel, so in this case the finger B that you show here, so the face grain and then the support, so in that case it parallel to support. So that is the two scenario, and you can see how you set up plywood relative to the support. So that's what the difference. So in there you can be able to go ahead to find out the shear, and this again the similar to table 13.6, you get that equation, and deflection also, and again this plywood. So compare on those three numbers, get the smaller, and in this case we can see that the bending governs, so that is 13.2 inch. So with that we can use or select the stuck spacing in 12 inches. Continue with the select well spacings, and because that 12 inch we can determine the uniform load on the stuck based on your select spacing for stuck. So you can determine And the same, use the same table 13.5. You can be able to determine the maximum span for the wells with bending, with shear, and with deflection. In this case, the shear governs, which is 21 inch, so the smallest one, so it governs, and it 21, easy to lay out in the real life. In the practical project, we use or select 18 inches or 1.5 feet for the well spacing. And that we can go ahead. The next step, select tie spacing. So you have 18, so you can determine the load on the wells. So that one is 900 pounds per foot. Apply the same bending, shear, and deflection from table 13.5. You can be able to determine the spacing for bending, for shear, and for deflection. And in this case again, the shear is governed 25.6. And 25.6, we select 24 inch tie spacing, which is 2 feet spacing. So with that one, we can, similar to the previous problem that have a lengthy video, and you can remember that we can check for the saw strength and check for crushing, and we can do the same in here. Check for the tie load. So the load equal to the well spacing times tie spacing times concrete pressure. We select previously well spacing is 18 inches, tie spacing 24 inches, concrete pressure is 600 pounds per square foot, so it will be get that 1800 pounds per tile. And the allowable load for the tie at the problem give us is 3000 pound capacity, so it's less than that. The actual is less than the allowable, so that's good. Okay, and now we check for bearings. There are two scenarios that we have to check: the stuck on the wells, and then the tie wedges on the wells. The stuck on the wells, and I demonstrate here, similar to the problem 3 in the previous lesson, where I demonstrate with more animations in there. So stuck are vertical, the blue one, and the wells are double 2x4, and horizontal, as you can see here. So the bearing areas is the contact between the stuck and the well. So there are two wells, so you have two, and each the cross section 2x4, the actual size is 1.5 inch times 3.5 inch for 2x4 cross section nominal size. So with that, as you can see, it will be 2, and the width of the stuck is 1.5, and the width of each wells 1.5. So that 2 of the wells, so times 2, so it's 4.5 inches square inch. So from that we can determine the load for each panel point, so that the red highlight there. So to have P load of per foot of stuck there, stuck vertical, and then well spacing, just that similar to the previous problem 3 of previous lesson. So we have 600 pounds per foot for the stuck load stuck, and the well spacing is 18 inches. Unit conversion, so we have 900 pounds. And then from that we can determine the stress, actual stress on the bearing contact between the stuck and the wells. So P over A is 900 divided by the areas of contact 3.5, 4.5, so you have 200 pounds per square inch, so PSI. That is the actual. The allowable that the problem gives us is 485 pounds per square inch PSI. So it's less than the actual, less than allowable. Perfect. And the next step, we need to check the bearing, that contact between the tie wedges on the wells. So what is the tie wedges? That from the finger there, you see the wedge and the wells have a contact, and the wells that they give you the with 1.5 inch Y wedges bearing on well. So it's the same exactly the Y of the wedge, same as the width of the cross section of the wells, so that we can be able to similarly we can be able to determine the bearing areas, and that is here 2, 1.5, 1.5, 4.5 inch square. And the tie load that we already determined, check for tie load, 1800 pounds per tile, that is the actual load. So we can be able to determine the actual stress, that in this case perpendicular face strength perpendicular to support, 1800 divided by 4.5, you get 400 psi, and that less than the allowable 485 psi. So okay, so this we done for problem 1, and as you can see, it's a lengthy process similar to problem 3 and challenging, but the step, and you can see if you follow step, you should be okay to solve for the problem.